In today's lecture, we're going to start some studies of the thermodynamic identity, and our beginning is going to be with a discussion of mechanical equilibrium and pressure. And of course, this is for thermal physics. We are teaching this out of Thermal Physics 5. Here it is. Shorter. All right, so far we've talked about the entropy for different systems like Einstein solids, ideal gases, black holes, and the two-state paramagnet. And then we've used the entropy expression that we've developed for those systems, and then from that we've found a function of the the internal energy as a function of temperature, and then from that the heat capacity at constant volume as a function of temperature. We've also talked about how you can go the other way, that you can find the entropy change for a process by using the heat capacities to solve for the entropy change. And that is from the expression ds is equal to q over t, which is equal to cv dt over t. But these, of course, are for constant volume processes. And there's not a lot of constant volume processes that happen every day. In fact, most processes that happen every day on planet Earth are constant pressure processes, right? Not constant volume. That's a little bit more difficult to control. And so we know that these constant pressure processes can cause an entropy change, and it would be helpful to be able to develop an expression for the change of entropy of a system for a constant pressure process. So what expression can we use for the entropy change if the volume changes and it's not a constant volume process? All right, so this is a little thought experiment that we're going to do here. Let's say that we have two systems, A and B, and we place them in contact and we allow them to come to equilibrium. So before, in our thought experiment, we just allowed them to come to thermal equilibrium, okay? But now what we're going to do is we're going to say that, say the system AB is enclosed. So that is fixed, AB's, its volume, its total internal energy, its total volume and total internal energy of the system AB is fixed. However, we're going to allow A and B to exchange internal energy and volume. The way that I kind of conceptualize this is to visualize a movable partition in between system A and B, okay? And so let's say that system A is there on the left, it's the green system. It has an internal energy UA, a volume VA, and hence an entropy associated with that SA. And then system B has energy UB, volume VB, and entropy SB. Now, the total energy is fixed. So U is equal to UA plus UB, that's a constant. U is a constant. The total volume is fixed. The total volume V is equal to VA plus VB. But UA and UB can exchange internal energies as long as the sum stays the same. And VA and VB can exchange volume, right? That partition in between A and B, in other words, can slide left-right here if the pressure in between A and B is not the same, okay? So that really is going to be the pressure, the quantity that will come to equilibrium. And this is kind of easy to see if you envision that movable partition there, okay? Let's say that you had a higher pressure of the green gas than you did in the orange gas on the right. That high pressure of the green on the right would push the partition over to the right, okay? And that means that the volume of system A would increase while the volume of system B would decrease, okay? So that's what we're talking about here. Now, when we allow systems to come to equilibrium with their internal energies, the thing that becomes the same is the temperature, okay? So when things come to thermal equilibrium, the temperature is the same. Now, if you allow the volume to exchange, right, if you allow that partition to move, if you allow that to come to equilibrium, and we'll call it mechanical equilibrium when that comes to equilibrium, the thing that stays the same then is the pressure. So if you put two systems in contact, allow them to exchange volume until they come to mechanical equilibrium, what will be constant at the end is the pressure. So through our little thought experiment, I hope that kind of makes sense to you, okay? So if you allow systems to exchange energy or volume, what's going to happen is that through that exchange, through that change, the entropy, the combined entropy of the system will also change. And of course, by the second law of thermodynamics, we know that for a closed system, our entropy will increase, okay? Our total entropy for the systems will increase. Now, the mathematical way of finding the relationship in between the entropy, the pressure, and the volume is shown here in this equation. P over T is equal to the partial of S with respect to V holding U and N constant, okay? So here on the left, we have the things that are the same when they come to equilibrium, the pressure and the temperature, because we're allowing it to exchange internal energy and volume. So the stuff that comes to be, the same once that happens is there on the left. And then what's happening is the entropy is changing, and as it comes to mechanical equilibrium, the volume will change. So we have partial S with respect to V on the right. I hope that's clear. Now we can look at this new equation and do a few things with it to make sure that it's a sanity check, I guess. So what we can do is look on the left and do a unit dimensional analysis, which is also a useful thing to do. So the SI units for pressure is the Pascal, which is the Newton per meter squared, and the SI unit for temperature is the Kelvin. So that means that on the left, P over T has units of pascals per Kelvin. Now on the right, we have an entropy change divided by a volume change. S over V, S has units of joules per Kelvin, and volume has units of meters cubed in SI. So the units on the right would be joules divided by Kelvin times meters cubed. Now a joule is a Newton meter. So that would be Newton meters divided by Kelvin times meters cubed. Then you have a meter canceling out, so you have a Newton over a Kelvin meters squared. But then a Newton per meter squared is a Pascal. So on the right-hand side, we have pascals per Kelvin. So that shows you that at least the units of that equation are right. Now another sanity check we can do on our equation, our new equation, is to apply it to a system that we already have an entropy expression for, like the ideal gas, using the saccharotetrode equation for the entropy of a monatomic ideal gas, which is shown here, right? So there's our entropy of a monatomic ideal gas. We can take the partial derivative of that expression with respect to volume and then see if it equals P over T. And if it does, then that's a sanity check, okay? So here's our expression for S. Now remember, when you take partial derivatives, you treat everything else like a constant, and then you just worry about the derivative with respect to the one variable. Now, I could try and take the derivative of this whole thing, but I'm also a little lazy, so I'm going to use a trick. And that's the definition of how things relate to one another in logarithms when they multiply. So the only explicit dependence of volume in this expression, this saccharotetrode expression, is the nk times the natural log of v. That one v, that's the only v in the whole expression, and the rest of this stuff you can treat like a constant. So remember that when you multiply things in logarithms, it's the same as adding two separate logarithms. So I can factor out, if you will, that v. So that becomes then nk times the log of v plus nk times the log of everything else. And then, of course, I also have that nk times 5/2 expression. But none of that has v in it, so I'm just going to put that over there. Now, if I take the partial of s with respect to v, looking at it this way, it's easy to do. I'm just going to have nk as a constant, partial with respect to volume of the log of the volume. That gives me 1 over volume. So this whole big mess here on the right-hand side just becomes nk over v. So the partial s with respect to v is equal to nk over v, which is equal to p over t. Well, is it? Yes, it is, because that's our expression for the state equation for an ideal gas. PV is equal to nkt. Okay? So that's our ideal gas law. Check. So that's another sanity check of our expression. Okay, so units check out. It works for entropy of a monatomic ideal gas. Okay. So we've got two ways right now. We've already talked about the true definition of temperature, right, which is the way that the entropy changes as you vary the internal energy, and that gives you partial s with respect to u, holding n and v constant, 1 over the temperature. And now we have this new expression for how the entropy can vary, and that one is p over t equals partial s with respect to v, holding u and n constant. Okay? So that's two ways the entropy can vary. Now, we can combine those into one expression. So let's just say that we hold the number of particles constant, okay? If we hold n constant, then our change in s, ds, would be equal to partial s with respect to v, holding u and n constant, times dv, plus partial s with respect to u, holding n and v constant, times du. This is from calculus, right? So it's the definition of a derivative. Okay, so now we plug our expressions in for what partial s with respect to v and partial s with respect to u are. Partial s with respect to v is p over t, and partial s with respect to u, we've already shown, is 1 over t. Okay, so p over t and 1 over t, plug that in. That means that ds is equal to p over t times dv plus du over t. So we can rearrange that and solve for du. And if we do, then we have a start on our thermodynamic identity. So here, du is equal to TdS minus PdV if n is fixed. All right? Okay, now, thinking about this expression a little further, it's tempting to say that Q is TdS because we've already kind of talked about that expression, right? ds is equal to Q over T. We've already talked about that. And then it's tempting to say work is equal to minus PdV, or d work is minus PdV, right? That's tempting too. And we've explained that that is true for compression expansion work. But if you look at this full expression, even though it's tempting then to say du is equal to Q plus W, and Q is TdS and work is minus PdV, it's really tempting, but it's not always true, so be careful. This is only true if, first of all, no other forms of work are done. Remember that the minus PdV expression doesn't encompass all forms of work. It only encompasses compression expansion work, right? That's done for gases. There's other kinds of work, right? There's lots of them. So if there's other forms of work in your change, then this expression won't work. It only works for fixed n. If you allow the number of particles to change, then this expression, this Q is TdS and minus PdV, that doesn't hold, okay? And it also only works if the changes in volume are quasi-static, so that the system is in mechanical equilibrium throughout the change. Now, anytime you hear the word quasi-static, you should think slow, okay? So this only works for very slow processes that are basically in equilibrium at each step along the way, all right? But you can use it as an approximation for some situations, and in those situations, it's really useful to think of it that way. You just have to have in your mind when that's okay to do and when it's not okay to do. All right. Now, what can we do to have a more useful expression for the change in entropy for systems? Remember, that was one of the whole focuses of this lecture. At the beginning, we said, oh, we have this great expression for the change in entropy. It's the integral of CV over T dt. But not everything's constant volume, so what do we do? Well, here we go, okay? Getting there. Remember that we said that we had the thermodynamic identity, and we can rearrange it this way. ds is equal to 1 over T times du plus PdV. Okay, now, way back when, we talked about the enthalpy. The enthalpy, H, is equal to U plus PV. And the enthalpy is most often used as an expression when you have a constant pressure process. Constant pressure, right? So dH is equal to du plus PdV for constant pressure processes. So we could rewrite this expression for ds as ds is equal to 1 over T times dH, where dH is the change in the enthalpy. Now, if I wanted the total entropy, I could integrate both sides of that expression. So I'm doing that here. Delta S, the change in entropy, would be the integral of ds. And then on the right-hand side, I would have the integral of dH over T. Now, I can break that out because here I've got some dependence on the temperature, usually in my entropy or in my enthalpy expression. So, applying my calculus knowledge here, I've got dH would be equal to the partial of H with respect to T, holding the pressure constant, times dt. So remember, we talked about the heat capacity at constant pressure, C sub P, and we said that the heat capacity at constant pressure was defined as the partial of H with respect to T holding P constant. So that means that I can set this expression equal to the integral of Cp over T dt. All right? Now, if you need to pause it and go back and look at those expressions again to realize that I'm telling you the truth, pause the video now and do that, okay? But otherwise, I'm going to proceed with this expression. Delta S is equal to the integral of Cp over T dt. All right? Phew. So now I want to do an example problem, okay? Realize that the third law of thermodynamics, for example, says that you have to have your entropy going to 0 as T approaches 0, right? And so what that means, one of the fallouts from that, is that your heat capacity can't be a constant at low temperatures. Your heat capacity has to decrease and go to 0 as temperature goes to 0. So this means that the heat capacity isn't a constant function for most materials, and you can measure what the heat capacity of a material is and see its temperature dependence experimentally. That's plotted here on the upper right for some materials: lead, aluminum, and diamond. Okay, so you can see that it looks like lead and aluminum are approaching that asymptote of 3 times R for a constant heat capacity once you get up to a decent temperature. But notice that they're nicely obeying the third law of thermodynamics and having their heat capacities go to 0 as T goes to 0. So that's all good. Okay. Now diamond's slower, okay? At room temperature, it's still not quite there, right? It's still not approached that asymptote for the nice constant heat capacity like we discussed Einstein's solids should. And it's got a linear dependence. And that's actually true of materials. They won't have that constant heat capacity for some situations. And you need to know how to deal with that. So that's what's covered in problem 30 of chapter 3. So here it is. The heat capacity of diamond near room temperature is shown in the figure, and it's approximately linear in T near room temperature. Okay, you could fit a line to that and have it work. So extrapolate that function, make it longer than it really is, and extrapolate that function to 500 Kelvin and estimate the change in entropy of a mole of diamond as its temperature is raised from 298 Kelvin to 500 Kelvin. Okay, so what we've got plotted here is the molar heat capacity of diamond. So this is all measured for 1 mole of diamond. So if I extrapolate a line from this, we won't have to worry about the 1 mole part because it's already 1 mole. Okay? Here we go. What I'm going to do is I'm going to use 2 points to make a line. So I actually put those little green dashed lines in there. This is a figure and table from your textbook, Schroeder's Thermal Physics. Okay, so but on top of that figure, I put those green dashed lines to help guide your eyes so that you can see that I'm going to use 2 points to make a line, get a function for that line, and then use that function for my heat capacity and integrate it to get the delta S. So that's my strategy. Okay, so the 2 points that I chose are the points at 300 Kelvin and 400 Kelvin, and based on that line I can estimate what the heat capacities at those 2 temperatures are. So drawing that straight line across, you can see that at 300 Kelvin it looks like it's about 6 joules per Kelvin, and at 400 Kelvin it looks like the value is about 10 joules per Kelvin. So those are my 2 data points. 300 Kelvin, 6 joules per Kelvin, and 400 Kelvin, 10 joules per Kelvin. Okay, I write it that way because the horizontal coordinate comes first, that's the temperature, and the vertical coordinate comes second, and that's the heat capacity. Now, remember, 2 points to make a line. You first find the slope, which is the rise over the run. Okay, so the rise here would be the change in the heat capacity, and the run would be the change in the temperature. So finding that slope m is 10 minus 6 divided by 400 minus 300, rise over run. The units of that would be joules per Kelvin, which is joules per Kelvin squared. Solving for my slope, I get a slope of 0.04 joules per Kelvin squared. Now, that's only one part of making the line. I'll also have to find the intercept. Remember, y is equal to mx plus b, so now I got to find the intercept b. All right? So that's going to be the intercept at 0 Kelvin, right? And so if I find the intercept at 0 Kelvin, that would give me 6 minus b. Now I'm going to use my slope equation, right? I'm going to take my 300 Kelvin data point, okay, and then I'm going to calculate what the heat capacity would be if I extrapolated a straight line back to 0 Kelvin. So I'm going to use rise over run again, and that would be 6 minus b divided by 300 minus 0. Joules per Kelvin squared. I set that equal to my slope, which is now known, which is 0.04. Then I just do some algebra. I would have 6 minus b is equal to 300 times 0.04, and then I would solve for b. When I solve for b, I get minus 6 joules per Kelvin. Okay, so that's what I've got. that means that my equation for the line is C sub P is equal to 0.04 joules per Kelvin squared times T minus 6 joules per Kelvin, right? Good. So now that I have my function for C, what I can do is I can plug that into my expression for the change in the entropy. Delta S is equal to the integral of Cp over T dt. So plugging that in, I have the integral of 0.04 times T minus 6 divided by T dt. Now when I simplify that, in the first expression here, 0.04 times T over T, the T's cancel out. And in the second expression, I get minus 6 over T. So what I'm integrating is, and now I plug in my limits, I'm integrating from the limit of 298 Kelvin to 500 Kelvin, that's what the problem asked, of 0.04 minus 6 over T dt, right? So integrating that expression, 0.04, the integral of that is 0.04 times T, and then the integral of 6 over T is the 6 times the natural log of T. So I have 0.04 T minus 6 times the natural log of T, and then I'm going to evaluate that expression from 298 to 500. Okay? So doing that, plugging numbers in, I end up with a change in entropy of about 5 joules per Kelvin with rounding to 2 sig figs for that change in entropy. Okay? And the way that I did that is all plotted out here, shown here. Now, that's our entropy change, and that's what the question asked, okay? But another question might ask you to find the raw entropy, the total entropy value at a certain temperature, okay? And that temperature that it asks you to find it at might not be the one displayed on the charts, which are in the back of your text and readily found online. So what you can do is you can take the value from the chart, which is the value of the entropy at 298 Kelvin for 1 mole of diamond. Okay, so this is an excerpt from the table at the back of your textbook, Schroeder's Thermal Physics. And you can read that for diamond, right, the entropy at 298 Kelvin and 1 bar is 2.38 joules per Kelvin. Now, if I take that value and add it to the change in entropy that I just calculated, then that would give me the entropy at 500 Kelvin, right? So that's what I've done here. I said that S is equal to 5 joules per Kelvin plus 2.4 joules per Kelvin, rounding to 2 sig figs, and that gives me an entropy of 7.4 joules per Kelvin at 500 Kelvin. All right? So that's how to handle it. That's how to use that expression. Delta S is equal to the integral of Cp over T dt. Okay, that's how to use that expression. And here we did it for something where the heat capacity varies with temperature, but you might have a problem, for example, where the heat capacity is constant with respect to temperature, and then it's a little bit more straightforward, okay? So it just depends on the problem. The functions may be different and all that kind of good stuff, but this lays the foundation for how to find the entropy for a process where you're changing something at constant pressure, though, okay? All right. I hope that was understandable and that you got it. Let me know if you have any questions, and I'll see you in